There are several new formulas that you will find in Chapter 5, Section 4. The formulas that we will be focusing on are the half angle and double angle formulas. In 5.4a, we will learn how to establish some identities and also use the half angle identities to find an exact value without a calculator. We will begin by deriving the double angle formulas for cosine. To apply the sum difference property, we will need to rewrite 2u as u plus u. Here is the sum difference property from 5.3. Alpha is u and beta is u, so if we apply the property, we will get. Next, we will simplify by replacing cosine of u multiplied by cosine of u with cosine squared of u, and sine u multiplied by sine u with sine squared of u. What we have found is one of the double angle formulas for cosine. There are three double angle formulas for cosine. Let's derive the other two double angle formulas for cosine. We can do this by applying the Pythagorean identity to find the other two double angle formulas. We just found that cosine of 2u is equal to cosine squared of u minus sine squared of u. This was our first double angle formula for cosine. We can apply the Pythagorean identity we learned in 5.1 to find the other two. If we get sine squared of u by itself by subtracting cosine squared of u from both sides, we will get Now we can replace the sine squared of u above with 1 minus cosine squared of u. By distributing the negative, we simplify, combine like terms. We have found a second double angle formula for cosine. Similarly, if we go back to the Pythagorean identity and solve for cosine squared of u by subtracting sine squared of u from both sides, we will get this. Now we can replace the cosine squared of u with 1 minus sine squared of u. Simplifying and combining like terms, we get 1 minus 2 sine squared of u. This is the third double angle formula for cosine. There are three double angle formulas for cosine. Having three double angle formulas for cosine will save us a few steps when using it to solve equations in the future. To prove an identity, start with two columns labeling them statements and reasons. Use either what's to the right or left of the equal sign for your first statement. I usually start with the uglier of the two sides unless there is an obvious property to apply. Sine of 3x is my given. You want to use what's on the other side of the equal sign for your final statement. Writing a first and last statement allows you to work in both directions. It also allows you to keep your eye on what you're trying to get to. I will work backwards one step by distributing the sine of x. Next, I would like to expand the sine of 3x. To do this, I need to replace 3x with 2x plus x. Using the sum difference property, I will expand sine of 2x plus x. Now I see some double angle identities. There is only one double angle identity for sine. I will replace sine of 2x with 2 sine x cosine x. The other double angle identity I see is cosine 2x. I have three options when making a substitution for cosine of 2x, as there are three double angle identities for cosine. If we look at what we're heading towards, we see that the only trig function contained in the expression is sine. This tells us we should use the double angle formula for cosine that is equal to nothing but sine. Making the substitution, I get this. The cosine of x plus sine x will remain the same. Next, I can simplify the left side. 2 multiplied by sine x multiplied by cosine x multiplied by cosine x is 2 sine x cosine squared x. I can also distribute the sine x. I can see that I want to get rid of cosine squared of x because I'm keeping an eye on what I'm heading to. I can use the Pythagorean identity sine squared of u plus cosine squared of u equals 1 to get rid of the cosine squared of x. Looking at the Pythagorean identity, I can get cosine squared of u alone by subtracting sine squared of u from both sides, which means cosine squared of u is equal to 1 minus sine squared of u. Making that substitution, I get everything else will stay the same. I will distribute 2 sine x and everything else will be the same. When we combine like terms, we finish building the bridge. We've met the other side. By factoring out a sine x, we arrive at the final statement. This concludes the proof. The half-angle formula enables us to find the exact value of an angle that is not on the unit circle. The half-angle formula for sine is as follows. We need to think of an angle measure that when it's divided by 2 equals 105 degrees. Sine of 105 degrees is the same as the sine of 210 degrees divided by 2. Unlike the angle measure 105 degrees, 210 degrees is on the unit circle. Substituting 210 degrees into the half-angle formula, we get. Next, we want to evaluate the cosine of 210 degrees. So we go to the unit circle at 210 degrees, and the answer to cosine is the x-coordinate. The x-coordinate at 210 degrees is the square root of 3 over 2. We now have a fraction within a fraction, so to simplify, we multiply the numerator and denominator by 2. Multiplying the numerator by 2 and the denominator by 2, we get the square root of a fraction is the same thing as the square root of the numerator over the square root of the denominator, which is now all we need to do is decide if the answer is positive or negative. The formula says plus or minus, but it does not mean the answer is both. We will use the acronym All Students Take Calculus to determine the sign of the answer. To use this acronym, we need to decide what quadrant 105 degrees is in. 105 degrees is in quadrant 2. In quadrant 2, sign is positive. Therefore, the answer to sine of 105 degrees is positive. Here is another example using the half-angle formulas. We want to find cosine of pi over 8. However, pi over 8 is not an angle measure on the unit circle. The half-angle formula for cosine is as follows. We can make this problem easier by converting pi over 8 to degrees. Here's a little scratch work. Starting with pi over 8, to convert, we will multiply by 180 degrees over pi. The pi's will cancel, and 180 divided by 8 is 22.5 degrees. I will now replace pi over 8 with its equivalent, 22.5 degrees. To use the half-angle formula, we need to think of an angle that when divided by 2 is 22.5. That angle will just be 22.5 doubled. Notice pi over 8, 22.5 degrees, and 45 degrees over 2 are all equal to one another. Now we can substitute 45 degrees into the formula. Using the unit circle, we will evaluate the cosine of 45 degrees. To find the answer to cosine of 45 degrees, you go to 45 degrees and use the x-coordinate. Our current answer is a fraction within a fraction. To simplify, multiply the numerator and denominator by 2. If we distribute 2 through the numerator and the denominator, we get the square root of a fraction is the same as the square root of the numerator over the square root of the denominator, which gives us this. The half-angle formulas say plus or minus, but our answer is not positive and negative. We need to decide if the answer is positive or negative. So we'll use the acronym All Students Take Calculus to decide. We are finding the cosine of 22.5 degrees, and 22.5 degrees is in quadrant 1. In quadrant 1, all trig functions have positive answers. So the answer to cosine of 22.5 degrees is going to be a positive answer. So our final answer is just positive.